Welcome back to the deep dive. Get ready to plunge into something fundamental, something you interact with every single day, probably without even thinking about it.
Yeah, absolutely.
We're talking about acids and bases. They're not just, chemicals stuck in science labs.
Not at all.
They're in your food, your cleaning supplies, and even incredibly inside you, making life possible.
These substances are absolutely everywhere, really driving countless chemical reactions. Understanding them is, well, it's key to unlocking so much of chemistry.
Like what?
Oh, everything from biological processes like, say, digestion to big industrial applications and environmental science, too.
Exactly. So whether you're maybe tackling grade 11 physical sciences or you're just super curious about the chemical world right under your nose, this deep dive is for you. We're going to explore what acids and bases fundamentally are, how they behave when you mix them, how we can identify them.
And why it all matters.
Yes, and why mastering these concepts is so important. Let's get into it.
All right, where do we start? Maybe with what's most familiar. Stuff you find at home.
Absolutely. Good idea. Think about the sourness of vinegar. That's ethanoic acid.
Sometimes called acetic acid, yeah.
Right. Or lemon juice. That tartness. Citric acid doing its thing. Even the acid in your stomach, hydrochloric acid, plays a massive role in breaking down food.
And on the base side, you've got things like baking soda, that sodium hydrogen carbonate used in baking.
Yeah.
Or washing sodium carbonate for laundry. Ammonia is pretty common in cleaners, like glass cleaners.
Right.
And then the stronger stuff, like sodium hydroxide or caustic soda. You find that in drain cleaners sometimes.
These everyday examples give us a hint, maybe, about some general properties.
Yep, they do.
Like acids often have that sharp, sour taste.
Yeah.
Though, big disclaimer here.
Oh, definitely.
Never taste chemicals in a lab.
Please don't.
But bases, they can taste bitter and often feel kind of slippery.
They do, yeah.
Yeah.
That slipperiness is actually because they react with the oils on your skin. Sort of forms a soap-like substance.
Okay.
But, taste and feel aren't exactly safe or reliable ways to ID chemicals.
No kidding.
So chemists needed more rigorous definitions, especially to figure out what's happening in reactions. There are a couple of key theories here.
Okay. The first one people usually learn is the Arrhenius theory, right?
That's the one, yeah. It was a great starting point, really focusing on what happens when these things dissolve in water.
So what's the Arrhenius idea?
Basically, Arrhenius said an acid is something that bumps up the concentration of hydrogen ions, H plus I, when you dissolve it in water.
Okay. H plus I.
And an Arrhenius base. That's something that increases the concentration of hydroxide ions, OH, in water.
Hydroxide, OH. Like sodium hydroxide, NaOH?
Exactly. When NaOH dissolves, it just releases those OH ions that are already part of its structure.
That makes sense for things like HCl and NaOH, but does it cover everything? What about ammonia, NH3?
Good question.
It acts like a base, right? It neutralizes acids, but it doesn't have an OH group in its formula.
Exactly. And that's a key limitation of the Arrhenius theory. It's really focused on water solutions and, well, specific formulas.
So it's not the whole picture.
Not quite. This is where the Bronsted-Lowry theory comes in. It offers a broader view and super useful for understanding way more reactions, even ones not in water.
Okay, Bronsted-Lowry. Tell me about that. What's the core idea?
It's all about the proton transfer.
A proton, like from a hydrogen atom.
Precisely. In chemistry, a proton is essentially just a hydrogen ion, H plus the Lowry. It's a hydrogen atom that's lost its electron.
Gotcha.
So the Bronsted-Lowry theory defines an acid as a substance that donates a proton. It's a proton donor.
Okay, so if an acid gives a proton, then a base must receive it, accept it.
Exactly. A Bronsted-Lowry base is a proton acceptor, and this definition works perfectly for ammonia, NH3.
How so?
Well, ammonia can accept a proton from another molecule, like water, for instance. We'll see that reaction in a bit.
This proton transfer thing, it feels much more, active than just making H plus or OH.
It is, like a chemical handoff.
Yeah, like a dance where protons get passed around.
That's a good way to put it. And it's really crucial for understanding how acids and bases behave, especially when they hit water. When acids dissolve in water, they ionize.
Ionize? How is that different from, say, dissociation?
Good question. Dissociation is usually when an ionic compound, like a table salt, NaCl, or sodium hydroxide, NaOH, just breaks apart into the ions it's already made of when it dissolves. Simple separation.
Right.
Ionization, though, involves a reaction with water where new ions are actually formed. For acids, it's about giving that proton to a water molecule.
Okay, so water itself is involved in the reaction.
Absolutely. Take hydrochloric acid, HCl. When it dissolves, the HCl molecule donates its proton to a water molecule, H2O.
And the water takes it.
Yep. The water acts as a base here, accepts the proton, becomes H3O plus hydronium. I've seen that. Right. And that's why you often see H plus and H3O plus used almost interchangeably when talking about acidity in water. The H plus doesn't just float around alone. It grabs onto a water molecule.
So the reaction is HCl plus H2O gives H3O plus
And what's left of the HCl? The chloride ion. So HCl plus H2O plus H2O plus AQ plus ClOQ.
HCl is the acid, water is the base in this case, and other acids like ethanoic acid. Same idea. Ethanoic acid, CH3COOH, also donates a proton to water. CH3COAQ plus H2O. Now notice this. H3O plus AQ plus CH3COO. See the double arrow?
Yeah, what's that about?
That means the reaction is reversible. It doesn't fully complete. Ethanoic acid only gives up some of its protons.
Oh, okay.
And that's the difference between strong acids like HCl, nitric acid, HNO3, sulfuric acid, H2SO4, which ionize almost completely.
They give up nearly all their protons.
Right. And weak acids like ethanoic acid, which only ionize a little bit in water. That degree of ionization is what determines their strength. Got it. So strong acids make way more H3O plus ions than weak acids, even if you start with same concentration.
Exactly.
Okay, what about bases in water then?
Well, the ionic ones, like sodium hydroxide, NaOH, or potassium hydroxide, KOH, they just dissociate. They break apart easily.
So NaOH just becomes Na plus AQ and OHAQ.
Precisely. They release the hydroxide ions they already contain directly into the solution. These are strong bases because they dissociate completely.
And bases without hydroxide in their formula, like ammonia again.
Back to Bronsted-Lowry. Ammonia, NH3, acts as a base because it accepts a proton.
Where does it get the proton from?
From water. Ammonia actually reacts with water. NH3AQ plus H2OL plus AQ plus OHAQ.
Oh, interesting. So water gives a proton to ammonia.
It does. Which means in this reaction, water is acting as the acid.
Wow, okay. And ammonia becomes NH4 plus O, the ammonium ion.
Right. And notice what else is formed. Hydroxide ions, OH. That's why ammonia solutions are basic.
And the double arrow again. So ammonia is a weak base.
Exactly. It only reacts partially with water. So strong bases dissociate completely or react fully to give lots of OH. Weak bases only do it partially.
Makes sense. And, looking at those reactions, especially the reversible ones, that proton going back and forth leads to another idea, right? Conjugate pairs.
Spot on. That's the next logical step. It's about looking at the before and after of that proton transfer.
What defines a pair?
A conjugate acid-base pair is simply two molecules or ions that differ by just one single proton, one H plus pair.
Okay.
When an acid donates its proton, the thing that's left behind is called its conjugate base.
Right.
And when a base accepts a proton, the thing it turns into is its conjugate acid.
Let's use the HCl and water example again. HCl plus H2O plus Cl. HCl is the acid. It loses a proton. What's left?
The chloride ion, Cl. So HCl and Cl are a conjugate acid-base pair. HCl is the acid, Cl is its conjugate base.
Okay, I see. And in that same reaction, water, H2O, acted as the base. It accepted a proton. What did it become?
The hydronium ion, H3O plus plus. So H2O is the base, and H3O plus, as the acid it becomes, are the other conjugate pair in that reaction.
Got it. Two pairs in one reaction. What about the ammonia one? NH3 plus H2O, NH4 plus OH.
Okay, you tell me. NH3 is the base, accepts a proton. What's its conjugate?
It becomes NH4 plus ammonium, so that's its conjugate acid.
Perfect. NH3 and NH4 plus are a conjugate pair.
And water, H2O. Here it acted as the acid, it donated the proton. What did it become?
It became the hydroxide ion.
OH.
So H2O is the acid this time, and OH, its conjugate base, are the other pair.
Hang on. So water was a base in the first reaction, forming H3O plus Sarah, and it was an acid in the second reaction, forming OH, the same molecule doing both.
Exactly. You've hit on a really important concept, amphiprotic substances, sometimes called amphiolites.
Amphiprotic, meaning?
Meaning they can act as either a Bronsted-Lowry acid, donating a proton, or a Bronsted-Lowry base, accepting a proton. It depends entirely on what else is in the reaction with them.
And water is like the classic example.
It's the poster child. Absolutely. Reacts with an acid. It's a base. Reacts with a base. It's an acid. Super versatile.
Are there others? Other amphiprotic things?
Oh, yeah. Ions can be too. Think about the hydrogen carbonate ion, HCO3, from baking soda.
Okay, HCO3, how does that work?
Well, it can accept another proton, acting as a base, to become H2CO3, carbonic acid.
Right.
But it can also donate the proton it already has, acting as an acid, and become the carbonate ion, CO32.
Fascinating. So it just depends on the chemical environment. Okay, speaking of reactions, let's talk about what happens when acids and bases react together more generally. Neutralization.
Yes, to the term, yes. Neutralization reactions. And they tend to follow predictable patterns, usually making a salt and water.
Now, when you say salt, you don't just mean table salt, NaCl.
Good point, no. In chemistry, a salt is basically any ionic compound formed from the positive ion of the base and the negative ion, anion, of the acid.
Okay, an ionic compound made from the leftovers, kind of?
Pretty much. So first pattern, acid plus a metal hydroxide. What do you get?
Salt and water.
Salt and water. Example, sulfuric acid, H2SO4, plus magnesium hydroxide, MgOH2.
Okay.
That gives you magnesium sulfate, MgSO4. That's the salt plus water. H2SO4 plus MgOH2, MgSO4 plus 2HQO.
Got it. What about acids with metal oxides, like rust reacting with acid?
Metal oxides work too. Acid plus a metal oxide also gives you salt and water.
Lovely.
Let's use hydrochloric acid, HCl, and magnesium oxide, MgO.
Okay.
2HCl plus MgO, MgCl2 plus H2O. Magnesium chloride, MgCl2 is the salt here.
Right. And the third one, the fizzy one, metal carbonates.
Ah, yes. Everyone loves the fizz. Acid plus a metal carbonate reacts to produce salt, water, and carbon dioxide gas, CO2. That's the fizz.
Like mixing vinegar and baking soda. That's acid and carbonate, isn't it?
Exactly. Vinegar is ethanoic acid. Baking soda is sodium hydrogen carbonate, which acts like a carbonate here. You get sodium ethanoate, the salt, water, and CO2 bubbles.
Cool. Another example.
Sure. Hydrochloric acid, HCl, reacting with calcium carbonate, KCO3, like chalk or limestone. 2HClAq plus KCl3 at KCO2AQ plus H2OL plus CO2G. The salt is calcium chloride, KCl2.
So we know what they are, how they're defined proton donors and acceptors, how they behave in water, these conjugate pairs, amphiprotic things, and how they react together. But, like, practically, how do we actually tell if something's an acid or a base safely?
Yeah, definitely not by tasting. That's where acid-base indicators come in. They're incredibly useful tools.
Indicators, like litmus paper.
Litmus is a classic example, yes.
Right.
Indicators are special substances, usually complex organic molecules, that actually change color depending on whether they're in an acidic or basic solution.
How do they do that?
Well, most indicators are themselves weak acids or weak bases. Let's say it's a weak acid indicator. Call it H-ion.
Okay.
H has one color. When it loses its proton, it becomes the ion N, which has a different color.
Ah.
So in an acidic solution, where there are lots of H plus ions around, the equilibrium favors the H-ion form. You see the acid color. But in a basic solution, where OH ions are removed, the H plus of the equilibrium shifts, more H-ion loses its proton to become E and I, and you see the base color.
So the color change is like a signal about the concentration of H plus or OH ions?
Exactly. It tells you whether the solution is acidic or basic. There's several common ones you need to know.
Like litmus, red in acid, blue in base.
Perfect. Litmus.
Yeah.
Red in acid, blue in base. Then there's methyl orange.
Methyl orange.
It's red in acids and yellow in bases.
Red and yellow.
Phenolphthalein. This one's quite dramatic.
Oh, yeah.
It's colorless in acidic solutions, but turns this bright pink or reddish purple color in basic solutions. Really obvious change.
Colorless to pink purple? Useful.
Very useful, especially for titrations, which is a way to measure concentrations accurately. And one more common one, bromothymol blue.
Bromothymol blue.
That one's yellow in acids and blue in bases.
Yellow and blue. Got it. It's amazing how chemists use these simple color changes to figure things out.
It is pretty clever. And you can even find natural indicators. You ever done the experiment with red cabbage juice?
I think I have. It goes all sorts of colors, doesn't it?
It does. Red cabbage contains pigments called anthocyanins, and they change color across a whole range of acidity levels, not just acid versus base. You get reds, pinks, purples, even greens and yellows depending on how acidic or basic it is. A great kitchen chemistry demo.
Very cool. Okay, so let's maybe try to wrap this up, pull it all together.
Sounds good.
We started by looking at acids and bases just around us,
Yeah.
Vinegar, baking soda, linking common stuff to their names and formulas like HCl, NaOH, CH3COOH.
Right, the familiar examples. Then we got into the proper chemical definitions. Arene is first making H plus or OH in water.
But then the more useful one, Bronsted-Lowry, all about proton transfer. Acids donate H plus S's, bases accept H plus X.
Exactly, and we saw how that plays out in water. Acids ionizing, bases dissociating or ionized.
You producing H3O plus or OH, which relates to whether they're strong or weak.
And that proton transfer led us straight to conjugate acid-base pairs the acid and the base it becomes after losing a proton, or the base and the acid becomes after gaining one.
Like HCl and Cl, or NH3 and NH4 plus 2.
Perfect.
Then we hit that really interesting idea of amphiprotic substances.
The ones that can play both roles.
Like water or the hydrogen carbonate ion, acting as acid or base depending on what they're mixed with.
Very important concept. And then we looked at the main reaction types when acids meet bases neutralization.
Right. Acid plus metal hydroxide gives salt plus water.
Acid plus metal oxide gives salt plus water.
And acid plus metal carbonate gives salt plus water plus carbon dioxide, the fizzy one.
That's the one.
And finally, how we actually see this stuff, the indicators. Litmus, methyl orange, phenolphthalein, bromothymol blue, changing color to tell us if it's acid or base.
These core ideas really are fundamental. They pop up everywhere. Understanding your own body chemistry, like blood pH.
Wow, yeah.
To industrial processes, environmental issues like acid rain or soil testing. It all comes back to acids and bases.
It really does show how connected chemistry is to, well, everything. Okay, so here's a final thought to leave you, the listener, mulling over. We talked about strong and weak acids and bases, but why? What is it about the actual structure of, say, HCl that makes it so eager to give away its proton, making it strong?
Well, something like ethanoic acid holds on to its proton more tightly, making it weak.
Exactly. And same for bases. Why are some much better proton grabbers than others? It's not random.
Not at all. The reasons are baked into the molecules themselves, the bonds, the atoms involved, the stability of the ions formed. It's a whole other layer of understanding.
Something to maybe explore next time.
Absolutely.
Yeah.
But getting these basics down, definitions, reactions, pairs, indicators, that's the essential first step.